Welcome all back to this last part of the lecture of today. Thank you very much for your participation. Christina, the space is yours.
Thank you. Okay, then we will continue with the last part of the workshop today. You can see that today the workshop is much faster because we don't have to make so much more code, but just run our code and check the results. Then it's much more easier today. Okay, so now we're gonna use a different estimator to compute the clustering of our sample. In particular, we will use the Langley-Salai estimator. And for that, the only addition that we have to make in our code is to compute the term dr. Again, the computation of dr is exactly as we compute dd, but we have to just make little changes. Then as long as you made correctly your code for computing dd, you are almost done with the correlation function. Then I'm going to show you how we can do this. Then this is the workshop 4. I just put this in a different order just to make more clear in the procedure, but the code is exactly the same as we had for workshop 3. Then I will upload this code in case this is useful for you. Then the first part then is to create the dr vector. Then I'm going to create this here in the same way as dd. I'm going to do this at the same time for both data catalog. Then this going to be dr, and dr2 is for the catalog with high mass. Then this is not actually needed anymore. Okay, this is my dr. I should actually put this after the dd creation, between dd and rr. Okay, I'm gonna put the code here. Then I'm gonna just copy again the dd, well, the first one, the dd term. Then this is dr. The only difference here is that we have to compute distances between the data and between the random catalog. Okay, then we just have to change the name of the variables when we compute the distances between the sources. That is one change. And the other change is that we have 2 different catalogs. Then we don't have to go computing the distance between the first one and all the other elements below that every time. Then if you remember, we were computing the distance between the galaxy in the position I with all the array starting in the position I plus 1. Then now, given that we have 2 different catalogs, we don't have to do that. And instead of that, we have to start in the position 0 here all the time. Then I'm going to put this in the code. Then this is for the lower mass, the low mass sample. And this is just, in this case, this is going to be the random. I think I call this in that way. Let me check. Yes, that is the name of the random variables. Then that is one change. And the other change is that here, instead of I plus 1, I have to start in the position 0 all the time. Then I'm always computing the distance between each galaxy in my catalog with all the random positions in the random catalog. That is the only difference, and then dr is done. Then here I'm gonna change also the names, and that's it. And I'm gonna to copy this again to create the R2, which is the same, but using the catalog of high mass galaxies. Then here I just have to use the number of sources of the second catalog that I defined here before for the high mass catalog, and just change here also the names of the variables. Yes, with a random, and then here is dr2 and dr2. Then I will print here the vectors dr and the vector dr2. Then I can share with you the numerical values for those vectors. And I'm gonna probably I don't have to compute everything now. Then I would just stop my code here to show you the values. It's taking a little bit more longer because I'm computing for 2 catalogs at the same time. I don't know why it's taking that long. Yeah, that is correct. Here we go. Okay, then it's done. Those are the numerical values for the DDR and DDR2. Then I wanna print this here, then you can see this better. Again, ignore the first and the last bins here because I just include those for my records. Okay, then this is the DR and DR2 that I'm expecting you to get. Then maybe you can try to work on your own and try to code this part and try to reproduce those numbers here. Then I'm gonna give you 10 more minutes to work on this part, and then we will continue with the plotting and with the inclusion of error bars. I'm gonna be here in case you have more questions. Okay, I'm back again to finish this last part of the workshop. Then hopefully you were able to compute the R and reproduce the numbers that I got. Then now the last step is just to compute. Did I share my screen? No. It's just to compute the estimator, the Langley-Salai estimator. Then, yeah, we already finished this part. And we have now to, I forgot in the point before to make the log-log plot showing the dr vector, but I did during this 10 minutes. Then I can show you the plot with the dr vector. Should looks like this, then very similar to the other dd and rr vector that you have done. Then I'm gonna upload also this plot in the web page. And now we have to normalize the vector dr. Then in this case, given that we have two different catalogs and we count number pairs for different elements all the time, then the number pairs is now in this case nd times nr. That is the total number of pairs that should be in our dr catalog. Then I will normalize this, probably here together with the others normalizations. Then in this case, I can normalize the vectors, dr and dr2. This gonna be the vector that we have, and then in the denominator, this is just nd times nr. Then the same thing here, but it's nd2 times nr. Then that is the normalization in this case. I think is that correct? Yes, that is correct. Okay, so here I'm gonna compute again the omega value, but now for Langley-Salai estimator, then I'm gonna put here ls for both samples, and this is well, this dd over rr minus 2 times dr over rr, everything normalized, and I think it's plus 1. Is that correct? Yes, minus and plus. Yes, that is the equation that I provide you in the workshop sheet. Then this is the same for the high mass catalog, but this is dr2, dd2, and the rest is the same. Okay, I'm gonna add error bars also. Then in this case, the error bars is still Poisson, but it's looks a little bit different than the other estimator. I provide you with the equations in the instructions. You can actually prove that this equation is correct. It's just the error in this case is 1 plus the correlation function that you measured, then this equation, and over the square root of dd. And here dd is the not normalized vector. Then you can actually prove mathematically that this is correct, because this is the estimator. You can just compute the errors on this by differentiating each terms. Then is basically error propagation then you can check that this formula is correct for the error. Then, okay, I'm going to compute this here. For the case of DD, no, this is 1 plus the estimator over the square root of DD in this case. And is the same for the other, but this is the high mass, and this will be DD2. Then that is a way to compute errors, and I'm gonna make the plot now. I think that is all what we need. We have to make the plot and run this for low and high dot. Then I'm gonna give you the last 10 minutes to work on this. In the meantime, I'm gonna run my code because this take like a couple of minutes. Then I don't want you to wait so long for the result. And when in 10 more minutes, I will show you the plot and we will discuss the results. Then I'm gonna stop sharing now. We'll be back in 10 more minutes. Okay, I hope you could finish your codes for the workshop today, and I'm just gonna show you the plot that I got. I'll share the screen. This should be here. Yeah. Okay, so let me open this again. So this is the natural estimator that we used, the simple estimator that I showed you before. And what I get for the Langley-Shalai estimator is this plot here. I see more noise measurement. I was not actually expecting that, but that could be because our random catalog is still too small. It actually has the same size of the sample, then that could introduce some noise. But in general, what I wanted to show you is that we, at least you can maybe focus on the red points for now. We get more or less the same measurements as before. This first point is around 0.3 here. The same for this case here, for the natural estimator. And then the amplitude is kind of similar. We find a similar trend. I'm not pretty sure why I'm getting those points too low, but they are also associated with very large error bars. Then I guess that my random catalogs are not that big to show you like a nice plot here, but you can get the idea. Then basically the estimator that we use should provide the same measurement. I'm gonna double check that I'm doing the plot right, but I think it is right. It's just noisy. And then here I'm asking about the differences at large scale versus small scales. And that question was only because the Langley-Shalai estimator should work much better at longer scales. Here in this exercise, we are tracing only until 100 arc seconds. Then we cannot really see very well this effect. But if you try at home and run your code with different binning or different theta values, you will check that in the case of the natural estimator, you start seeing that the signal will be more flat at larger scales. And this is not will not happen in the case of the Langley-Shalai estimator, in which you will see here a power law, very like a more steep power law to say. Then the natural estimator will be a little bit more flatter here in this part. And this is mainly because this estimator don't work very well with the edge. Then at large scales, you will note that the Langley-Shalai estimator make actually a better job. Sorry that this is not very clear in this plot, but you can run your code again and check with different values. But that was the main message that I wanted to make here. Okay, and we are done with the workshop today. Then I'm gonna stop sharing. It's also 6 already, or 6 for me, 12 for you. Then probably you want to have some lunch.
Thank you very much, Christina. Yeah, here is lunchtime, and it's start to be something that you feel. So thank you very much, Christina, for the lecture of today. I want to remember you all, the participants, that tomorrow is the last day of the school. So we will have our last lecture and the last set of exercises, and then we are going to be done for this year. So I expect to see you all tomorrow in the last day of the school. Christina, thank you very much for your time, and see you tomorrow.
Thank you. See you tomorrow.